Stan Gibilisco here with a little discussion about the various amplifier classes for vacuum tube radio frequency power amplifiers. Now in this playlist, Teach Yourself EE Miscellany, I made a couple of videos early on having to do with classes of amplification, but those videos dealt with transistors, solid-state devices. Here I'm going to deal specifically with vacuum tube type power amplifiers because that is the subject of this whole series. In particular, it applies to radio frequency power amplifiers. Well, we have the same class names as we have with transistors. A, AB1, AB2, B, and C. Now I'd like to go through each one of those very briefly so that you'll have an understanding generally of how they work. What you're looking at is a graph, a hypothetical generic graph of the plate current versus the grid voltage in a vacuum tube. More negative grid voltage is to the left, more positive grid voltage or grid bias is to the right. This is under no signal conditions. So if we vary the grid bias in a vacuum tube but don't apply any signal whatsoever to the input, we'll get a plate current of 0 up until we reach the point known as cutoff. Same basic principle as you would find in a bipolar transistor, but a vacuum tube more nearly coincides with the behavior of an N-channel junction field effect transistor, so this would be more like the pinch-off state of affairs in that type of a device. If we continue to reduce the negative grid bias and eventually actually make it positive at some point, the plate current will increase until it begins to level off, and then any further increase in the positive grid voltage or reduction in the negative grid bias will not cause any further increase in plate current. That is called saturation. You never really want to saturate a tube any more than you want to saturate a transistor. So how does this work? Notice there is a straight line portion of this curve right here. If you bias the tube right in the middle of the straight line portion of this curve under no signal conditions, well, let's redraw that curve, and you bias it right there in the middle. Let's suppose you just bias it right here. That is Class A operation, and if you apply an input signal, the waveform will go up and down like this as the grid voltage varies with the input signal. And assuming that you don't have too powerful an input signal, you will always stay on the straight line portion of that curve. So that type of bias is sometimes used for audio frequency power amplification, like you would find in a guitar amplifier, or the type of amplifier you would use for a popular music band. A lot of bands like vacuum tube amplifiers because they say that they produce a richer sound than transistorized amplifiers do. Well, I don't have a whole lot of experience with that, but I can tell you that Class A operation right here, this is Class A, is never really used for radio frequency power amplification, because in radio frequency power amplification you don't need to worry so much about keeping the waveform in the straight line portion of this curve. Let me just redraw that curve a little more carefully here. I still am confounded by the behavior of this Windows Journal program. It just seems to have a mind of its own. Well, try that again. Bear with me, I'll manage. There's a curve. It kind of curves and then goes in a straight line and then kind of curves. Okay? This is the cutoff point right here. If you bias the vacuum tube a little further on down towards cutoff, you get class AB operation. Now, there's a difference, a distinction between AB1 and AB2. When you apply an input signal to a class AB1 amplifier, the waveform the input signal takes the tube into the non-linear or curved part of this curve, so it takes it out of the straight line portion, but it doesn't take it all the way to cutoff at any point during the input cycle. In class AB2, more like down here at the lower point, the wave does go past cutoff for part of the cycle, but a good deal less than half of the cycle. Radio frequency linear amplifiers typically operate in class AB1 or AB2. The RF waveform itself, that is to say the signal wave, does get distorted by this type of operation, but the modulation envelope, that is to say the voice print or whatever other modulation, amplitude modulation you may apply, music, voice, whatever, remains faithful to the input modulation envelope. So although the amplifier is not linear for the waveform, it is linear for the modulation envelope. I don't know where the word envelope comes from. I think it probably means that somehow or another you're enveloping the information in some kind of encoded fashion. I guess that's what it must refer to. So, like a wrapping sort of thing. I don't know exactly, but class AB1 and class AB2 are commonly used for what they call linear amplifiers. Now, once in a while, you will also find a linear amplifier operating in class B. Class B is biased right at cutoff so that the input waveform is half and half. Half out of cutoff and half in. So as a result, you get kind of a half wave rectification of the RF waveform. But if you design a class B amplifier very, very carefully, you can still make it linear for the modulation envelope. So that's class B. Now class C, just as with the transistor, you apply a DC grid bias in such a way as to take the tube past cutoff. Then the input waveform only goes into the conduction mode for a very small part of the cycle, sometimes only a few % of the cycle. You need a significant driving power in order to make a class C amplifier actually amplify. Otherwise, it won't amplify. It will literally attenuate the signal, or if you don't apply the waveform powerfully enough to get it out of cutoff, you won't get any output at all. A class C amplifier is never linear. Never linear. So, class C radio frequency power amplifiers are not useful for any kind of amplitude modulated signal. You know what I'm going to do? I'm going to completely close out that Windows journal and just open up a whole new file. Now, in a Class C operation like this, here's the graph again. Grid bias on the horizontal axis, plate current there. This is the characteristic curve, and you're biased right here. You can use a Class C amplifier as an RF power amplifier for any signal mode where there is no analog modulation, and that includes CW or Morse code. It includes phase shift keying. It includes multiple frequency shift keying. It includes radio teletype, and it includes FM. So Class C amplification is in fact used in some radio frequency power amplifiers. And I remember one that was used for CW and radio teletype at the old ARRL, American Radio Relay League station W1AW, that used a peculiar kind of tube called a 250TH. It looked like a light bulb with a wire sticking out of the side of it. And that was a Class C amplifier. The interesting thing is that in regards to the efficiency of an amplifier, that is to say the ratio of the plate power, the ratio of the RF power output to the plate power input, that's the efficiency, is highest in a well-designed Class C amplifier, sometimes as much as 70%, meaning that you might have a plate power input of 1,000 watts to a well-designed Class C amplifier and get 700 watts out of it. For Class B, typically more in the order of 60%. For Class AB, 50 to 60%. And for Class A, sometimes only 25%, 25 to 35%. So if you are able to operate an amplifier in Class C, go ahead and do it. The only thing is that you will need a lot of driving power in order to make it work. You need a significant drive to make a Class C amplifier function properly. But it's still a good design, and with a vacuum tube like the old 250TH, I wonder if they've still got that thing down there in the basement. Maybe you should Google on that and see what you get. Google on the phrase vacuum tube and then 250TH as a separate word, and see if you can get a picture of one of those things. It is a weird looking tube. Looks like something out of that Lee DeForest might have originally concocted. So that is just a little bit of I kind of had to go for a while on this video. Hope you managed to last through it all. Stan Gibilisco signing off for now. Until next time, so long.